In this presentation we will look at a brief introduction to atomic layer deposition, ALD, and the processes involved, what plasma enhanced atomic layer deposition, PEALD, is and how it is similar to ALD but adds some more options, the capabilities and limitations of PEALD, and concluding with what might lie in the future. And so we start with Moore's law, and here we have a generic plot of Moore's law. This law has driven companies, especially Intel, to keep increasing the transistor density, thus reducing the size of their devices. Because of this, materials and deposition techniques have been pushed to their limits. It is by pushing these boundaries and techniques such as ALD and PEALD have come into their own. And so, firstly, what is ALD? It is, as the name suggests, a method of depositing layers that are as thick as a layer of the molecule being deposited. It relies on the surface chemistry of the substrate reacting favorably with the gaseous precursors. The desired result is that the precursor reacts with the substrate and a layer is deposited. To start looking at the processes of ALD, firstly we take a substrate and place it in an evacuation chamber. Into this chamber, a material in gaseous state called a precursor, shown here in blue, is added to the reaction chamber. This precursor reacts with the substrate and forms a layer on the substrate. After this precursor has been absorbed to the surface, any excess is vented from the chamber. At this point, the second precursor, shown here in red, is added to the reaction chamber and reacts with the layer deposited on the substrate. This creates another layer on the surface and the reaction chamber is again evacuated. This process is repeated until the required film thickness is achieved. And so it is time to look at the qualities of ALD. It is a self-saturating process where the precursor reacts with the substrate. It does so with excellent adhesion and low thermal stress. The substrate is covered evenly due to the reaction of the substrate with the precursor and the self-limiting nature of the process. It can be used to put deposit on challenging surfaces such as Teflon, graphene, and gold. However, this method has some limitations. Some materials take significantly longer to deposit. Chambers must be vented effectively in this process lest precursors mix and create deposits. Not every material is physically possible to deposit in this manner. Some substrates may require to be functionalized for reactivity with the precursor. Also, some precursors require a higher temperature to be reactive with the substrate. This leads to variations in ALD, one of which is PEALD. A way to describe the difference between ALD and PEALD is by looking at the process window and how PEALD supplies sufficient thermal energy for a chemical reaction. Each precursor requires a temperature at which it will react with the substrate and thus be deposited. However, higher temperatures can cause materials to decompose or prevent any deposition. Thus, the growth window lies between the minimum activation energy and the point at which materials start to decompose. The work around that PEALD is based on is that the precursor is excited into a plasma in a local area, and this plasma is passed over the substrate without heating the whole system. This prevents decomposition of substrate materials. In the diagrams here we have two chamber systems used in PEALD, a capacitively coupled plasma-based PEALD system and an inductively coupled plasma-based remote PEALD system. In the capacitively based system, the plasma is made between the shower head and the stage of the chamber, where the plasma is created on top of the substrate. In the inductively coupled plasma system, the plasma is created and then passed over the substrate. PEALD suffers from conformity issues. The SEM images of the vias shown here exhibit excellent conformities for the thermal ALD in image A, while the PEALD in image B shows conformity that is much poorer. Poor conformity of PEALD is attributed to radical or ion recombination within the nanoscale vias. However, PEALD should not be discounted as a deposition method. One example may be found by looking at MOS capacitors with platinum electrodes. Measurements of capacitance, CV and IV were taken. They showed the accumulation of capacitance value for PALD, hafnium oxide, is greater than for thermal ALD, resulting in the smaller capacitance equivalent thickness. That is 1.2 nanometers for PALD and 1.3 nanometers for thermal ALD. Interface state densities represented by distributions of interface traps was approximately 2.5 times greater for thermal ALD when compared to PEALD. Leakage current of PEALD, hafnium oxide, was also smaller than that of thermal ALD, as shown in graph B. All these results indicate that in this case that the overall quality of the PALD was better than for the thermal ALD. In general, we should make a brief comparison between ALD and PEALD. This table summarizes the main points. PEALD will typically have a lower deposition temperature and thus can preserve the substrate from damage. PEALD allows a broader range of possible materials to be deposited, but also presents more complicated reaction chemistry. Film density for PEALD is higher but potentially sacrificing conformity. PEALD can have a higher throughput, however, being a plasma can damage some films. PEALD is an in situ plasma treatment and also has additional growth parameters. And so, in conclusion, generally the conformity of PEALD is inferior to that of ALD. However, the seeming disadvantage in conformity can be used advantageously. Very small penetration into the porous loci dielectrics was observed when tantalum nitride barrier was deposited using PEALD. This trait could be beneficial for low leakage copper metallization. The use of plasma during PEALD can lead to various beneficial effects on the nanoscale thin film deposition and on their physical properties. However, compared to thermal ALD, additional issues remain to be solved, the complexity of the equipment and processes being a major one. Over the last 30 years there have been relatively few papers on PEALD when compared to ALD. This is an area that may get more attention in the coming years. And these are my references for this presentation. Thank you.